Alright, so we're going to talk today about exponential functions, exponential equations. So just based on the name alone, what do you think we're talking about? Things that have what? Exponents, obviously. So we're talking about exponents. The difference between that is, for instance, here's some examples of exponential equations. So I have y equals 2 to the x, y equals 3 to the x, and y equals 4 to the x. So they're not just exponents, it's actually, what do you think is the difference? Because like x equals or y equals x squared technically has an exponent. But what's the difference between that and this? It's a little slight, very difference. You got to be kind of paying attention. The difference is your x, your variable, is in the exponent. Does everybody see that? So like over here, y equals x squared, your exponent's always going to be 2, right? Your exponent's always going to be 2, and then what changes is this, so it's always going to be something squared. Does that make sense? But like for instance here, it's y equals 2 to the x power. Your base of the exponent's always 2. What changes is your exponent. Okay? Have you guys ever seen the word, not in math class, the word exponential? Like what does it mean? The word exponential, but not like in math terms. Like how could you use that somehow? Not regarding math. You guys ever heard of something like on the news they say like the crisis grew exponentially or something like that? What do they mean by that? Rapidly. That's exactly what it means. It means rapidly. So for instance, look at this graph right here. These are exponential graphs. There's two types of graphs. There's growth and then there is decay. Okay? So look at this growth graph. So notice that it's y equals 2 to the x, y equals 3 to the x, y equals 4 to the x. Okay? So notice what's happening. They're all going which way? Up. They're all going up. But notice it's not like a line, because a linear equation, technically, a linear equation goes up, right? Like a straight line goes up. But what's the difference? Like a line goes up at the same rate, right? It's always going up. That's why it's rise over run, right? But an exponential function, it goes up, just like what Kaylee said, it goes up rapidly. It goes up exponentially. Does that make sense? Okay? So when we see these functions, this is kind of how they act. We're not really going to get too far into the graphs. I just wanted you to see what they look like. Okay, so this is y equals 2 to the x, 3 to the x, 4 to the x. So basically, they all grow exponentially. They grow fast. Or if they're decaying, they die or they come down exponentially as well. Okay, so let's start with the basics. These are some algebra 2 concepts. We have rules. We have rules for exponents. I'm kind of trying to see if you remember them, okay? So I have some rules for exponents. The first rule says, if I have A is just anything. A means any base, right? It could be anything. It could be 2, 3, 4, 5, 10, a million, X, anything. Let's say A squared, and then I'm multiplying by A to the third power. Do you guys remember what that rule says to do? You add the exponent. So this becomes a to the 2 plus 3, which eventually becomes a to the 5th power. Okay? Does everybody remember that rule? So when you're multiplying things that have similar bases, what do you do to the exponents? You add them. Okay? Rule number 2 says if I have similar bases, if I have two things that have exponents with similar bases, let's say a to the 7th power, and this time I'm dividing by a to the 3rd power. Does anybody know what the rule says to do to your exponents? You subtract them. So this actually becomes a to the, it's always the top minus the bottom, the a to the 7 minus 3, which actually becomes a to the 4th power. Okay, so far 2 rules. When they're multiplying, you add the exponents. When they're dividing, you subtract the exponents. Third rule. You don't see this a lot, but it happens. If I had, let's say, a squared, so something that already has an exponent, like a squared, and then I raise it to another exponent. Okay, so what do you do when you have an exponent raised to another exponent? You multiply them. So this actually becomes a to the 2 times 4. It's kind of like distribution, right? Which becomes a to the, becomes a to the 8th power. Okay? So when you have, the rule is when you have a base with an exponent already, raised to another exponent, you just multiply the exponents, okay? And you can combine them to one base. Those are not new, correct? Everybody remembers those? I think they were Algebra 2, maybe Algebra 1 rules. Okay, something that you might not know, but we can work with easily. What happens if I have a base with a negative exponent, okay? So first of all, you never want negative exponents in your answer, okay? So you can work with negative exponents, as in, like if I needed to multiply, I can multiply. If I need to add, subtract, whatever, I can do that with it as a negative. But in the end, my final answer should never have negative exponents, okay? So you have to fix that. So Ramiro thinks he knows, how do I fix a negative exponent? Good. So first you got to do one thing first. So what you do is you have to make sure that everything is in a fraction, okay? So right now I have a to the negative 2 power. It's not a fraction, but how do I make anything become a fraction? I put it over 1. So I'm going to put it over 1. And then I'm going to flip it. What is that called when you flip a fraction? You take the reciprocal. You take the reciprocal. So what's going to happen is I'm going to flip this, and it's going to become what? 1 over a to the now positive 2. Does everybody understand that? Okay? So when you have a negative exponent, the way you make it positive is basically you take the reciprocal of it, and it turns positive. We use this a lot in calculus. Okay? So this is a rule that we're going to continue to use, not just in pre-calc, but in calculus as well, for those of you moving on to calculus. Okay? So when you have a negative exponent, to make it positive, you take the reciprocal. And actually, it works both ways. Say you have something that's a fraction. And it already has a positive exponent, which is great, but you don't really want to work with it as a fraction. Well, you can turn it into a non-fraction by flipping it, but then now the exponent's negative. Does that make sense? So it's like what I told you. You can work with a negative exponent, you just don't want it in your answer. So sometimes it's helpful to make it negative just so I can work with it, and then later on I'll switch it back if I have to. Okay? Number 5, actually very useful as well in calculus. What do you do when you have a fractional exponent? So the rule is kind of like this. A to the 1/2 is the same thing as the square root of a. A to the 1/2 is the same thing as the square root of a. Here's the actual rule. The rule says this. If you have a base and you have a fractional exponent, you have a base and you have a fractional exponent, you can turn this into a radical simply by, it's always, the denominator is always the root, and then the numerator is always the exponent on the inside. Does everybody see how that works? Okay? So the denominator is always the root, and then the numerator of the fraction is always the exponent on the inside. So this is the actual rule. Let's go back to the one I just gave you. It's a to the 1/2. So that means that what's usually out here, there's a 2. Don't all square roots technically have a 2 there? We just don't write it, correct? And then the same thing over here. This would be a to the first power. Again, everything has a first power, but we don't write it. Does that make sense? So let me kind of give you just a quick example. What if I gave you a to the 2/3 power? Then that, if it were a to the 2/3 power, what would that become? What is that called? How do you say that? You either say the cubed root, or you can literally just say the third root, right? You can say third root, fourth root, fifth root. So you can say the cubed root, the third root of what? A squared. Does everybody see how that works? Okay? So this is just one of those rules. Now, this especially comes in handy in calculus because also, just like the other one, it works both ways. If I have a radical, I can switch it to a rational exponent. Okay? Why would I want to do that? Because sometimes I don't want to work with radicals. Okay? I don't want to work with radicals. So if I just switch it to something that has a rational exponent, then that's usually easier for me to work with. Okay? And then finally, I do have a rule that I did not start here, but it's very important. It's this. If you have any base to the 0 power, anything, literally anything, people, to the 0 power is always equal to what? 1. Okay? So, I can give you a pop quiz right now with 100 questions. And I can say, what's 2 to the 0 power? Your answer is 1. What's 10 to the 0 power? Your answer is 1. What's 1 million to the 0 power? The answer is 1. Does everybody got that? Anything to the 0 power is equal to 1. Got it? Alright, so these are my rules of exponents. So we're going to use these a lot. So these 3 you should have already known. 4 and 5 maybe you knew. 6 you should have known too, but you got to just keep those in mind. Alright? So we are working with exponents. So I'm throwing this in there because it's very important that we understand this, okay? So we have this symbol E. I know it's just a letter. So you know how variables can be basically anything, right? Variables can be X, Y, Z, sometimes A, B, whatever, blah, 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 blah. One letter you'll never see as a variable is the letter E. Why? Because E, like pi, is actually a number. Okay? When you see something like 2 pi, pi is not a variable, is it? You can't replace pi with anything. We already know pi is what? Approximately 3.14159, right? So this actually just means 2 times 3.14, and I can actually get a number out of that, right? So E is the same way. When you see E, it is not a variable. It is a number. Does everybody understand that? It is a number. It's approximately 2.718282. I'm not asking you to memorize that. I'm just letting you know that it is a number. It's a constant. Okay? It's called the natural base. It's called the natural base because it happens a lot in nature. Okay? It happens a lot in nature. This base, this natural exponential function happens a lot in nature. Like, for instance, population of insects, growth of plants, and stuff like that. Okay? So when we see E from now on, we don't think of it as a variable. It's a number. Okay? Alright, so all of that comes to this. So here's the important part. Here's the important part. When I have exponential equations, just like anything else, if there's a variable like x, I should be able to solve them. Okay? I should be able to solve them. So, the way I'm going to do that is something called the one-to-one property. So, I have something called the one-to-one property. So, let's start with example A. It says 9 equals 3 to the x plus 1 power. 9 equals 3 to the x plus 1 power. So, first of all, does everybody agree that this is... Alright, so does everybody agree that this is an exponential equation, right? Again, what makes it an exponential equation? Not that it has an exponent, that what's in my exponent? An x, okay? So remember, it's not that it just has an exponent, it's that there's a variable in my exponent. Has everybody got that? So here's what I have. I have 9 equals 3 to the x plus 1, okay? And if I asked you to solve, what do I want to know? I want to know what x is. I want to know what x is, okay? So how am I going to do that? I'm going to use something called my one-to-one property. Okay? My one-to-one property says if the bases on each side of an equation are equal, we can ignore them and set the exponents equal to each other to solve. Okay? So it says if the bases on each side of an equation are equal, then we can ignore them and set the exponents equal to each other in order for me to solve. Okay? I'm going to give you a couple seconds to copy that. Alright, so I know I shouldn't have to say it, but when I say the word base and exponent, everybody understands what I mean, right? Base is the number at the bottom, and exponent is the number at the top, correct? Or in this case, the equation at the top. So when I say if the bases on each side of an equation are equal, okay, I'm looking at my equation right here. What's the base on my right side? 3. What's the base on my left side? 9. Actually, what's the exponent to that right now, to the 9? If it was 0, remember, if it was 0, it would say 1. So it's not actually 0, it's what? 1. Does everybody agree with that? So I have 9 to the first power equals 3 to the x plus 1 power. So does my one-to-one property apply to me right now? What does it say? If the bases on each side of the equation are what? Equal. What was the base of this one? 3. What was the base of this one? So are they equal? No. So then the question is, can I make them equal? Okay, can I make them equal? Can I express perhaps 9? Can I rewrite 9 as a base of 3? Meaning 3 to any power, to some power? Is 3 to any power 9? Yeah, what? 3 to the second power. Does everybody agree with that? So then here's what I'm going to do. I'm going to say, look, I'm going to take this equation and say it's actually 3 squared equals to 3 to the x plus 1 power. Everybody see what I did? It's the same exact equation, correct? Because 3 squared is 9, right? And then this, and the other side is still just 3x plus 1, 3 to the x plus 1. Now, why would I do that? Because my one-to-one property says if the bases on each side of the equation are equal, what can I do to them? Ignore them, and I can set the exponents equal to each other. So basically, since both of my bases are 3, I'm just going to ignore them, and I have a new equation. My new equation says that 2 equals 2x plus 1. Does that make sense? So then, good. Now it's just an algebra problem. Kaylee says subtract 1, so x is equal to 1. And you can always go back and actually check. If x is 1, if I go back in here, so this says 1 plus 1, which is what? So 3 squared is equal to, see how that works? Okay, does everybody see how that works? But again, it only applied when what? When I was able to rewrite it in the same base. Does that make sense? Good. It can only work if the bases can be equal. Does everybody got that? Okay? Do me a favor. Why don't y'all try B on your own real quick? Try using the same kind of concept. I'll give you a couple minutes to try that. Okay, let's see how you did here. Okay? So I have 25 is equal to 5 to the x minus 3. Okay, on the right side, of course, what's my base? 5. On the left side, what's my base? 25. Okay, so are the bases the same? No, not yet. But can I express 25 as a base of 5? Yeah, 25 is really what? 5 what? 5 to the second power, right? 5 squared is 25. Does everybody agree with that? Okay, so I have 5 squared, which is equal to the 5 to the x minus 3. We good with that? So now that my bases are the same, basically what can I do? Set the exponents equal to each other. So then I have a new equation that says what? 2 equals x minus 3. And then now solve for x. What would I do? Add 3, x is equal to 5. And again, I could pretty much double check that. If I go back and plug in 5, 5 minus 3 is what? 2. 5 squared is equal to 25. Does everybody see how that works? Pretty simple. We get what we're doing? Let's try a couple more. Okay? Let's try a couple more. Okay, so here I have e to the 2x minus 1 equals e to the third power. So I have e to the 2x minus 1 equals e to the third power. You guys notice something? So e is a number, but more importantly than that, they're already the same, right? They're already the same. So then, since my bases are already the same, I'm really just looking at my exponents. So what equation am I really just looking at? And then now, guys, algebra solve for x. What would I do? Or, well, you're just kind of guessing at that point, but so how would I solve for x? I would add 1, which would be 2x equals to 4, and then divided by 2, x is equal to 2. Okay? So now I know x is 2, and you are correct. If I plug in a 2 here, 2 times 2 is what? 4 minus 1, which of course is, so it would be e to the third power. See how that works? Because okay, so you're just plugging numbers in. You see what I'm saying? Like, there's a difference between you trying numbers out and me finding the actual number. You see what I mean? Because what if 2 didn't work? My problem is this. What if my answer is a fraction? Most of us will not try and think about plugging fractions in, right? We like to stick to whole numbers. So that's why I'm saying solve it, because if your answer is a fraction, there's probably no way you're going to guess that it's a fraction, okay? So just work with it. Part D, see the same situation, right? My bases are what? Already the same. They're both e. So then my equation is what? So now, this one's a little different. Why? I have x's on both sides, guys. So let's go back to algebra. If you have x's on both sides, what's the rule? You have to move one towards the other, okay? You have to move one of the x's towards the other. It doesn't technically matter which one you move. You'll get the right answer as long as you do the math correctly. So in this case, I can move the 2x, or I can move the 1x. The good rule of thumb, though, just a helpful hint, is always try and move the smaller one. Why? Because then you don't have to deal with negatives, okay? So you're going to get rid of the x. And how do you can't just write it over there. Don't just combine them, because then people will want to say, oh, that's 3x. No, it's not. How do I get rid of this 1x? I subtract a 1x, okay? So that it cancels here, but 2x minus 1x is just what? X minus 5 equals to negative 3, and then now solve. So x is equal to what? Negative 3 plus 5 is 2. We good? So when you have x's on both sides, don't forget, move one towards the other. Again, technically it doesn't matter which one I moved, but always try and move the smaller one towards the larger one, so that I can not have to deal with negative numbers. Okay? We good? So does everybody see how this works? Okay? So does anybody have a question for me? There's a burning question, somebody maybe? Like, when it comes to problems like this? Nobody thought of it? Nobody said, well, what if I can't switch them? Like, what if I can't make them the same base? Do you think that's ever going to happen? Absolutely. Right? What if instead of this, what if instead of 9 it said 8? Is there a way for me to express 8 as 3 to some power? No, right? So what ends up happening there is that's going to be our next, actually 2 lessons from now. It uses something called a logarithm. You guys ever heard of logarithms? Okay, so we're going to use logarithms to help us with that. But in this case, with today's lesson, I'm giving you all the problems that you can switch, okay? So your assignment is going to look more like this, okay? Your assignment is going to look more like this. What this is basically the same thing, guys. It's just the combination of the rules that you should already know mixed with the solving, okay? So it's the rules you already know mixed with the solving, okay? So like, for instance, I have 10 to the negative 3x times 10 to the x equals 1 over 10, okay? So on the left side, what are these two things doing? They're multiplying, and you have a rule. Your rule says if they're multiplying with the same base, what do I do to my exponents? You add them. So I can actually make this just to be 10 to the what? Negative 2x, right? Because negative 3x plus 1x is negative 2x. Agreed? So I have 10 to the negative 2x equals to 1 over 10. Now, as of right now, are my bases the same? No, they're not. This one is 10, and this one is 1 over 10. But remember the rule I told you that technically, couldn't I think of this as 1 over 10 to the first power? So it's a fraction. And I said, well, sometimes you don't want to deal with fractions. So how can I make a fraction a non-fraction? Or how did I get a fraction in the first place? It was what kind of exponent do you think? It was a negative. So this was a negative, but I made it positive by making it a fraction, right? So then I can actually switch it back. So this would become 10 to the negative 1. Does everybody see how that worked? 10 to the negative 2x. So 1/10 is really 10 to the negative 1. Okay? Now are my bases the same? Yes. Now that my bases are the same, now I can get my new equation, which says what? Negative 2x is equal to negative 1. And then now solve for x. Negative 1 divided by negative 2. Well, first of all, negative divided by negative is going to be a positive 1/2. Because it's negative 2 over negative 2, so those cancel. The negatives cancel, so it's just 1/2. Right? Where did I lose? Right here, Kaylee? So, right now, this is technically, the base is 1/10, right? So, any fraction you can think of as the bottom part having a positive exponent. And your rule number 4 is this, right? If you have a negative exponent, to make it positive, you switch it, you flip it. But it also works the same way. If you have a fraction and it's a positive exponent, you can flip it back and it'll have a negative exponent. That's basically what I just did. So I said, look, I have a fraction I don't want to deal with. So if I slip it back, it's 10 to the now negative 1 power. And then now that my bases are the same, I can just get my equation and solve. We good? Any questions? All right, let me give you